Hey class, Mr. Mohidian here with a video to help further explain and understand the concept of a logic diagram or a circuit involving logic gates, which help us to connect the idea of conjunction, disjunction, etc., and those abstract propositional logic statements we saw, along with connected to the idea of electricity and computers and understanding how to program logic. So the three symbols we saw at the end of class were these. These are electrical circuits, or logic gates rather, that are involved in electrical circuits or logical circuits, and they correspond to the following ideas. This one is called a NOT gate. Remember, its propositional logic statement symbol is this. This is an AND gate, and it corresponds to this symbol in logic. And this is our OR gate, which corresponds to this one right here. We saw some other ones in class on the little handout that I gave you, so just as a preview, or they won't show up in this video, but just to keep these in mind, if you combined an AND gate with a little circle at the end, and that circle is sort of adopted from this thing right here, that'll give you a NAND gate, not AND. You take the OR and you negate it, so now you have a NOR gate. Excuse me, and the XOR gate, which is not negated, but the XOR gate looks much like the OR gate, except it has this little extra loop here to indicate that it's exclusive OR. So that would be XOR, and you can probably guess, you add a little circle, and you have XNOR. But for the present moment, focusing on the three above, NOT, AND, and OR will be okay for this video. So we're going to look at two different things. We're going to look at, one, how do you actually draw a diagram to help us address more complicated problems that become quite difficult to do with a traditional truth table with an electrical circuit, and vice versa. How do we look at a circuit and figure out what is its propositional logic expression or Boolean expression? So this statement says, excuse me, not P and Q or R. Not P and Q or R. So there's two halves to this problem, and they're not the same size, but they are two different parts. There's this half, and there's this half, right? And they are joined, they're connected by the logical operator called OR. So let's start there. One basic idea here is to start from the inside out, so to speak. So starting with that OR, let me try to color code this a bit. Starting with this OR, I'm going to draw that here. And there's two things feeding into it, and these two things are the two halves. Well, one of the halves is very simple, and that's just R, right? So that would just be this symbol here. R is being directly fed into the OR gate. The other half has its own sort of compound action there. It's a NOT AND, which if we knew the symbol, we could combine them, but let's not jump ahead necessarily. Excuse me, I'm sorry about the coughing here. We have a negation of this statement here. So at some point, P and Q are going to be joined together. So thinking further back to the beginning of the problem, beginning of the circuit rather, P and Q are ANDed together, so to speak. So you have P and you have Q, and they're joined together by an AND gate, which looks like a D. And that output is right away negated. So we're going to make it pass through a NOT gate. And if I simply connect with the other end of the circuit, that's now ready to feed into the OR gate as we needed it to. We often put a different variable at the end here to sort of show that the output of this entire circuit, we often put X or some other kind of variable just to show that P, Q, and R, depending on what their values are, will produce either a 1 or a 0, depending on what, of course, as mentioned, their original values were. So this would be the circuit that corresponds to this statement. Not P and Q, so P and Q is red, negated in green. That's being fed into the OR gate along with just plain old R. Let's take a look at another one. Alright, so this one also has two halves, and it's sort of lopsided, so that's often makes the problem a little bit easier, frankly, in my opinion. So this is once again an OR gate, and we're ORing with R and then a bunch of other stuff. So let's see. Let's start there with the OR gate. That would be this. It's going to bring an output here of x, and the two things feeding into it are R and then this other business. Now, this is sort of a convention that we often use in logical diagrams and engineering and computer science. Because this thing is kind of long, it's going to require sort of a longer, a bigger part of the circuit, whereas R is quite small. So I'm going to add what's called like a delay line to sort of show that R is going to travel along this path, and it'll meet the result of the electrons coming through the longer portion here. So this is just sort of a delay to add some simultaneity to our circuit. So R is being fed into the OR gate along with all of this business, which at its basis is an AND statement. So we're going to need an AND gate. And what are we ANDing together? Well, we're ANDing together a P and not Q. So we're starting with P and Q. We typically just start with our original inputs. P is ready to go right into the AND gate. So P goes into the AND gate. Not Q, however, the Q that we start with has to turn into not Q. So before it passes to the AND gate, it has to become not Q. So Q goes through a NOT gate and then passes through the AND gate. All we then have to do is to go ahead and connect it to the OR gate that we already had earlier. And there you go. P and not Q, or R. And this circuit, if you put in some inputs, will produce either a 1 or a 0 depending on what those inputs are. One more in this direction, then we'll look at the other direction. This one says A and B or C and D. So that's a little bit complicated. The letters are a little bit different, but nothing we can't address. So starting again from the middle here, the fundamental operator here is an OR gate again. So draw myself a little OR gate, producing an output. The two inputs are our two halves of the problem. We have this piece, and we have this piece. So let's look at the red one first. It's on top at least. So we have A and B. So A and B are two of our inputs. They're going to be feeding into an AND gate. An AND gate, I suppose, if we want to be grammatically accurate. And they're ready to pass through to join up with the OR at the very end there. We also have C and D joined up in much the same way. So C and D, two of our other inputs, they're being joined at the hip, wedding bells ringing, with another AND gate. And they're ready to be fed into the OR gate. So, not so bad actually. Looks quite colorful. So now we're ready to look at the opposite direction, being able to look at a logical diagram and figure out what is it actually trying to convey. Okay, so this one, starting sort of at the end here, is an AND gate, right? This is an AND gate. So I know that my two halves of the problem are going to be split apart by an AND statement. Whoops, an AND statement. Let's track the path of one of our electrons or electrical circuits. A is coming into this, and then it's immediately turning into not A. And that's one of our two inputs into our AND gate. So not A would be one half of our problem. Not A. The other part looks a bit trickier, so let's follow the path backwards here. Let's see. We have two things that are joined together via an OR gate. So I'm going to group these together. They're going to be separated with an OR gate. The two things being fed into that OR gate are B, and B is going in directly, so that's ready to go into our statement here. Let me do that here in purple. Here's B. B is being ORed with what used to be C, but has now turned into not C. So it was C, and it immediately became negated. So B or not C. Not A and B or not C. I have one remaining one for you to do if you want a challenge. So see what the logical diagram for this particular one would look like. It's kind of tricky, but I'll leave it to you to figure out if you wish. Alright, I'll see you in class.